Okay, so let's start our class. So we are going to start today chapter 3, DSP course, chapter 3. Okay, so chapter 3, digital signal processing. So as you can see from the slide, chapter 3 is what? The transform domain representation. Okay, so transform domain representation of discrete time signals and systems. It says what? Transform domain representation. Previously, we have seen time domain representation of discrete time signals and systems. Like chapter 2, we have discussed difference equation, convolution sum, and many other concepts about discrete time signal and systems based on time. We use the variable n, sampled or discretized time n. Signal represented as a function of n. System equation like impulse response h as a function of m, n, we call it impulse response. System represented as a difference equation which relates input x of n with output y of n. This equation, we call it a difference equation, also as a function of n. So previously, everything is time domain. Now, very important chapter in DSP is called transform domain representation. But you will not find it like this in the textbooks. The textbooks we have followed now, Prokins, digital signal processing by Prokins. Also, you'll find this transform domain representation as separate chapters. Z transform, one separate chapter. Discrete Fourier transform, another chapter. But here, in this chapter, I organized this chapter so in three main parts. So the first part, 3.1, as you can see, it's about date transform. As I said, date transform, you'll find it as one separate chapter in books, ASP books. But in here, in this course, in this chapter, we are going to take date transform, first part, discrete time Fourier transform, second part, and discrete Fourier transform. DTFT and DFT are different. So DFT will be a third part. So special algorithm, which is used to compute DFT, what we call it FFT, fast Fourier transform, also will be discussed in this chapter. So it's very important chapter as electrical and telecom engineering students, to go through this important chapter, transform domain representation of discrete time signals and systems. Okay, so what will be our first topic? Date transform, this chapter, date transform. So date transform As the name indicates, it is we are transforming a signal from time domain to Z domain, transforming a signal so our signal in time domain as a function of what? As a function of n is transformed into another domain x of z. Okay, x of z. Another variable, we call it z. So this is, as the arrow indicates, bidirectional, which means the signal as a function of time can be transformed from time domain, this is time domain representation of a signal, into what? Into Z domain. To the reverse, you can transform Z domain representation x of Z into x of n. So it's bidirectional. So it's transforming x of n to x of z. That's why we call it z. That's why it's called z transform. It's equivalent form of Laplace transform in analog signal cases. In analog or continuous time signal systems, you know what Laplace transform means. We call it what? Laplace transform, S, variable S. But here for discrete time signal systems, we call it Z transform. So we use the variable Z transform. So Z transform, now the question first question you may ask, why we need to transform a signal from time domain x of n into Z domain x of z by using this equation here. As you can see here, x of n is given, the time domain representation of our signal, multiplied by another signal z to the power of minus n, take the summation, it will give us x of z. So we are transforming x of n to x of z. So the first question, why we need to transform signal from x of n to x of z? But it's not only for signals. Z transform is for, we use it for what? For analysis design of the signal part, plus we use it for analysis and design of discrete LTI systems. It's used for analysis of signals. It's used for analysis of systems also, LTI systems. We'll come the system part later. Now let's start from the signal part. So let's answer the first question: why we need to transform x of n to x of z, the first place, using this equation. How to use this equation will come to that. But before that, I want you to understand what is the meaning of this Z transform. So to do that, so when you see this, this a discrete time system with difference equation here, this equation, what we call it, what it's called, difference equation. We have discussed this difference equation in chapter 2. So y of n is equal to this is x is the input, y of n is the output. So this d is delay element. So y comes here, delayed by 1, it becomes what? Y n minus 1, right? Another delay, y n minus 1 delayed by 1, it will be n minus 2. Again delayed by another delay element. So here we have yn minus 3. The output path is delayed by 3 times here. Then here we have a multiplier. So yn minus 3 multiplied by how much? 0.86. You can see here. Okay. Plus, these are other circuits, plus yn minus 2 times, this is multiplier, minus 2.65. You can see it here in our equation. Plus, this is addition, yn minus 1 multiplied by how much constant? 2.78. All this plus together with input comes from this side, it will give us output. That's the difference equation means. Okay. So another equation here, another system. So you see the difference equation here. Y of n is equal to x of n comes from this direction. Here we have if y of output delayed by 1. So yn minus 1 multiplied by how much? Multiplied by 1.68 goes this direction. So where is that? This part. Okay. Again another delay. Yn minus 1 again delayed by 1. It will be yn minus 2. So in our equation yn minus 2, what is the multiplier? Minus 0.94 multiplied by this. Go back to the input, added with the input adder here, it will give us the output. So that is the difference equation. Equation for this particular system with input x and output y. Internally, the system constructed using what? The simple components. Delay element or memory element, these are multipliers, and these three are adders, and this is also another multiplier. So we have seen this difference equation in chapter 2, right? System represented in difference equation form. Equation which relates input and output as a function of what? As a function of n. N is time. We call it time domain analysis of signals in systems. So now look here. The first case, when you apply input signal to this system, what type of input? It is impulse. X is impulse. You know what is impulse means? Delta n. It is only one, amplitude 1 at n is equal to 0. Here it looks like analog, but we are talking about samples. So discrete time, you have to keep in your mind. So when you apply impulse as input, what will be the output? The output is called impulse response h of n, right? You can apply any input here, but in this particular case, we apply input impulse, output will be, we call it what? Impulse response h of n. So what type of impulse response this system gives us? It is oscillation. But it is damped oscillation, decreasing oscillation, right? You see the amplitude decreases for samples, for different samples. Still, we are talking about the function of n. How about this system? Same impulse input applied, but you see this system has different impulse response. It's also decreasing oscillation, but decreasing, but it's higher frequency compared with the first system. So what do you understand? Each system has its own impulse response. Impulse response, very important function. How do you find impulse response? By applying impulse as input, you can find what is the impulse response of that particular system, h of n. Okay. Now, so in this case, you see the system's impulse response are decreasing oscillations, right? Uh, how about these two? So in this case, what is our conclusion? Both systems are stable systems. Why we call it stable? Both the two systems are stable. Why? Because we have, for bounded input, we have what? Bounded output. BO stability. Okay? The output decreases. It does not increase continuously. If your output increases without any limit, the system is unstable, right? So both these two systems with difference equation you see here, they are stable. How about these two systems with difference equation here and difference equation here? So you can see the system. How do you get this difference equation? Y delayed by 1, we get what? When you delay y of n, it becomes yn minus 1. Here is a multiplier. Multiplied by how much? 2.8. So you see here, yn minus 1 multiplied by 2.8. Again, this yn minus 1 delayed by 1. It will be yn minus 2. Then multiplied by how much? Minus 2.68. The second, and again, yn minus 2 delayed by 1 more. It will be yn minus 3, which is multiplied by 0.87. So all this feedback from the output side added here together with what? With the input here. Input plus these three outputs, delayed outputs, will give us the output. So that's the difference equation we have discussed. Okay. So how many delay elements in this system? Memory units 1 to 3. How many multipliers? 3 multipliers. How many others? Sorry, 4 multipliers and 3 other circuits to construct this system. Very simple discrete time system with difference equation given here. Is it the system LTI or not? Linear time invariant. Check the coefficients. The coefficients of this difference equation, if they are constant, if the difference equation has constant coefficients, the system, we call it LTI, linear time invariant system. So this system is LTI. How about this system? Look, coefficient of x of n, 1, constant. This coefficient, 1.75, constant, right? This coefficient, negative 1.02, constant. If you have constant coefficients, the system is LTI, linear time invariant system. Previously also, all the coefficients are constant, so the systems are LTI systems. How about stability? This case, if you apply again as input the impulse, as input, as you can see, it is impulse amplitude 1 only at 0. We get output, we call it impulse response. All right. So impulse response in this case, it is what? It's growing oscillation. Previously we have seen impulse response is decreasing oscillation, but in this case, as n goes to infinity, the output increases continuously. When you take this system also with difference equation here, again, it's growing oscillation with high frequency. Again, it continuously grows. So what's our conclusion? Both these systems are unstable systems. So one important reason why we use Z transform is to identify whether the systems are unstable or stable. Without going to check the impulse response, you can determine whether your system is stable or unstable using what? Using Z transform. I'm explaining why Z transform, very powerful, important mathematical tool in DSP. It has so many applications in digital signal processing. Here we are discussing only few. So when you transform a signal X of n using this simple power series formula, which is summation of X of n with what? X of n is a input signal, then the power of minus n is power series, is a sequence. So multiply these two, take summation, it will give you X of z. So why we need to Z transform? First, to identify whether a system is stable or not. So you can see here, this system linear time invariant. Yes, because you see the coefficients are constant. So is it stable or not? It is what? It is a stable system, because when you apply input, the impulse response, as you can see, is decreasing. Okay, it is what? In this case, is it oscillating? It's not oscillating. The first one, here it is oscillating, right? Oscillating. But here it's not oscillating, it's exponential, decreasing exponential. So you can say the system is stable. So Z transform, it will used to easily identify whether a system is stable or unstable. Okay. Next, and the most important application of Z transform for me is the next one. Okay, so when you transform x of n to x of z using this formula, we use it to identify. First part, as I said, we can determine whether a system is stable or unstable from Z transform. But the most important thing, when you transform a signal x of n into x of z using this simple unilateral Z transform formula, it is used to identify the presence of increasing and decreasing oscillations in your signal. A signal, a discrete time signal, may consist of what? May consist of decreasing oscillations. It may consist of increasing oscillations. It may consist the signal, composite signal, right? It's not single frequency. It's made up of many frequencies, oscillations. So which type of oscillation, which type of exponentials present in the signal? Okay, which means you can decompose a signal. As you can see here, this sampled signal sequence is equal to 1, 2, in this case only we write 4 components. Okay, any signal decomposed into different components using what? Using Z transform. So what does it mean? We use Z transform to determine the frequency response of a system. And what are the identify the presence of exponentially increasing or exponentially decreasing oscillations in your signal, whether x of n consists of exponentially increasing or exponentially decreasing oscillations. You can determine by using Z transform. Okay. So what we can do using Z transform? We can determine by identifying the presence of increasing or decreasing oscillations in which in the impulse response of the system, we can say the system is stable or unstable. What does it mean? So in the first case, what type of oscillation exists in the impulse response? If you convert h of n into z domain, it becomes what? H of z, right? We can, as I said, we can transform signals, samples from time domain to z domain. If it is any signal x of n, you can transform it into capital X as a function of z. In this case, h transformed into capital H of z. So when you transform it into z domain, transforming a signal or a system impulse response from time domain to z domain, it will help us to identify what type of oscillation is there. It is exponentially decreasing like this, or exponentially increasing like this in your impulse response, in your signal. What type of oscillation is there? Is it decreasing or it is increasing? Is there any oscillation or not? Is there any DC signal in your signals or not? This frequency component identification can be done achieved by Z transform. That's why it's very, very important. So the first one we have seen, by taking Z transform, we can achieve these two things at the same time. What's the first one? We can identify the presence of increasing or decreasing oscillations in the impulse response. If it is decreasing, you can say the system is stable. If the oscillation is increasing, you can say the system is unstable. Second thing, as I said, second one and the most important, we can identify the presence of what? The presence of sinusoidals in the system or in the signal. We call it frequency response. It's called frequency response. That's very important. So not only identify the frequency response of the system, we use Z transform to design also. To design a system with the required frequency response. If you are asked to design a system with this type of frequency response, you can use Z transform. Okay, so when you do examples, it will be clear for you. So let me give you one example. So let's say what is x of z? X of z is equal to summation, the formula n from 0, we use capital for z domain, okay, up to infinity, the sequence x of n multiplied by z the power of minus n, okay. This is what we call it unilateral z transform. Now z is a variable here. We are transforming x of n to x of z. Okay, so let's see example. Let's take x of n, our discrete time signal. discrete time signal, sorry. So let's take 2, this is my arrow, -3, -1, and 4. So let's take Z1. What is Z? Z is complex frequency variable with e raised to j omega. So R is the attenuation, omega is angular frequency. Now we'll come to this later. Let's take now Z1. Z is equal to 1 means frequency omega is equal to 0. Okay, so it's what type of signal? It is a DC signal. Frequency 0 signal means DC signal. Okay, so what is Z the power of -n? It will be all ones. DC signal all 1. Okay, amplitude because this is amplitude part. This is the frequency part. Z is a complex variable with amplitude and frequency. So now the amplitude is 1. So it's constant DC frequency the omega e raised to j omega. When frequency is 0, e raised to 0 is what? It is 1. Okay, so a DC signal with frequency 0. Now let's do this transformation, Z transform. This is our sequence x of n. Now Z is a DC signal with frequency 1. Now when you do this Z transform, we are determined similarities, correlation between what? Between x of n and Z the power of -n. Between these two, what type of similarities? This one comparing with what? With a DC signal. What is there any DC signal, DC frequency, which means frequency 0 in your signal x of n? How we do that? By doing what? Z transform. Okay, let's start from this simple case and we'll come to the general case. So look here, what you have to do. First, multiply x of n with Z the power of -n, right? You see the formula is multiplication. So 2 times 1, it will be 2. -3 times 1, Z is always 1. -3 times 1, -3. -1 multiplied with 1, -1. 4 times 1, 4. First, in Z transform, we multiply the input signal with Z the power of -n. Multiplication of the two. X of n is given. Z is 1, all 1, DC. When you do this, multiply and take summation, which means we are doing what we call it correlation. It is called what? Correlation. Very important in signal and DSP, correlation. Correlation means how much these two are similar, similarity. Okay. I'm comparing now what? My signal with the DC. Z now we take only one particular Z, which is a DC frequency. As I said, Z is complex frequency. We'll come to that. Now, after multiplication, what's the next step? Summation. Add this. What will be the result? The result is -1. It will be 2. Okay, let's take another signal x of n. 3, minus 3, again 3 minus 3. Now, when you do correlation of this second signal with the DC, what do you get? 3 times 1, 3, plus summation, minus 3 times 1, minus 3. 3 times 1 again, we get 3. And finally, minus 3 times 1 here, Z is always 1. It will be minus 3. So what is the summation here? 3 plus minus 3, 0. 3 minus 3, 0. This is 0. So what we understand? When you compare the first x of n with DC, we get how much? We get 2. Which means this signal has what? This signal has a DC. Okay, it has a DC signal. How about the second one? This x of n. When you correlate, when you do Z transform, it will give us what? It gives us 0. So what does it mean? When you see the second signal, sample 3, positive 3 here. What's the next sample? Negative 3. Negative 3. Then positive 3. Then finally negative 3. So this is the second one, right? So how much is the average for this signal? DC. DC means the average. Here you see positive 3 minus 3. It will be average 0. Positive 3 here, negative 3 here. Average 0. So that's why there is no DC component in the first signal. DC component means, is there a DC value, average value in this part, the second part? No. How about the first signal? It gives us what? When you do correlation using Z transform, it will give us 2. That's the DC value. How much this signal related to the DC, it gives us 2. Okay. So they transform. It's very important mathematical tool which is used to identify the presence of exponential increasing, exponential decreasing sinusoidals, exponential DC, what type of frequencies components your signal has. In this particular example, I have showed you, I take Z DC, I choose Z what? DC, and compare with my signal x of n to check is there any correlation or similarity with the DC with my signal using what? Using Z transform. Okay, so you can see how important Z transform is to identify what type of frequencies. If you take sinusoidal, okay, pure sinusoidal sine wave, do Z transform with your signal and check the relationship. What type of sinusoidal signals exist in your signal? Amplitude, what's the frequency of that sinusoidal? Is it decreasing oscillation? It's there in your signal. Increasing oscillation, is it there in your signal? What type of components your signal has can be determined from the transform. So that's why you can consider it as very important concept in DSP.